So let's do a Taylor polynomial of degree 1, 2, and then 3 for our function y equals e to the x. Okay, so clearly, first thing we need to find is f of 0, um, given our function f of x equals e to the x. So e to the 0 is just 1. And then we need to find out, our first derivative, second derivative, eventually our third derivative. So our first derivative, f prime of x is e to the x. F double prime of x also e to the x. This is a pretty easy function to work with since all of its derivatives are just itself, the only function for which that's true. So we know that f prime of 0, f double prime of 0, f triple prime of 0 also all equal 1. So now that we've done that sort of preliminary work, we can find the following. So if I wanted to find P1, P1 is this part of the equation. P1 is f of 0. F of 0 is just 1 plus f prime of 0 of x. Well, f prime of 0 is also 1, so plus 1x. And that's P1. That's a polynomial function of degree 1. If I wanted to find a polynomial function of degree 2, well, it has P1 in it, so we have 1 plus 1x. But now I'm going to add this section, including the x squared. So plus f double prime of 0 is 1 over 2 factorial, which we write as 2 times 1 times x squared. So that's our polynomial function of degree 2. Of degree 3, we're going to have all of this that we had already. But then we're going to add our third degree. We're going to add our cubic to it. So we're going to add this piece. So we add that. When we add that piece, we have f triple prime of 0, which we've already calculated. It's 1. So plus 1 over 3 factorial. 3 factorial is 3 times 2 times 1 times x cubed. And now we've got our 3 Taylor polynomials. One of degree 1, one of degree 2, and our last one of degree 3. And what I was trying to say earlier, hopefully it was clear, is that as n increases, so as n increases, our polynomial function improves. And we can see that on the next slide. So if we look at each of these graphs with respect to e to the x, here we have our P1, P2, and P3 approximation. And we're looking, again, we're looking around x equals 0. So if we zoom in on that x equals 0 area, for for x is right around x equals 0, P1 is okay. P2 starts getting clearly better, and P3 looks pretty excellent for a long time. So again, as n increases, as we look at greater uh, values of n, so bigger polynomials, the bigger the polynomial is, the better it will approximate. So let's do another example around y equals sine x. So very quickly we can generate p sub n of x. It equals f of 0 plus f prime of x plus f double prime of x over 2 factorial x squared plus f triple prime of x over 3 factorial x cubed plus dot 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 dot. So what we need to do is we need to find some of our initial values. So let's go ahead and do that. Let's find f of 0. So sine of 0 we know is 0. So we've got this initial part. And let's take its derivative. So f prime of 0 equals, well, the derivative of sine is cos at 0. Cos of 0 is 1. And f double prime of 0, well, the derivative of cos is negative sine, and we're evaluating at 0. That's 0. Let's take the third. f triple prime of 0. Well, the derivative of negative sine is negative cos of 0. Negative cos of 0 is -1. And we're going to start getting some interesting patterns here. So f quadruple prime. And once we start getting big like that, we write it like this. F, the fourth root, our fourth derivative, evaluated at 0. Well, the derivative of negative cosine is positive sine of 0, which is 0. And we're going to follow this pattern of 0, 1, 0, -1, 0. So because sine just oscillates between sine, cosine, negative cosine, repeat. So we know that f of 5 of 0 would be positive cos of 0, which is 1. So we're repeating again. So let's just get a couple more of these. f6 of 0 equals 0, and f7 of 0 would be -1. Okay, so let's now go ahead and find our Taylor, or the other name for it is the Maclaurin polynomials for y equals sine of x. So we can have, let's start at n, for n equals 1, we know that f of 0, so for n equals 1, we're looking at this chunk, and so p1 would be 0, because f of 0 is 0, plus f prime of x, well, f at 0, so these should all be zeros. So f prime of 0 is 1, so plus 1x. So that's my n equals 1 Taylor or Maclaurin polynomial for y equals sine x. If I do p2, I'm going to have 0 plus 1x plus, and now I'm going to look at the second derivative at 0. Well, this is an interesting case. The second derivative at 0 is 0. So we'd get 0 over 2 factorial times x squared. And that whole chunk is 0. So there really isn't a P2. What about P3? Well, P3 would be f of 0, so 0 plus 1x plus 0. So that's all this term. Plus, now we're going to look here. The f triple prime of 0. Well, f triple prime of 0 is -1 over 3 factorial times x cubed. Simplifying that, we get 1x minus 1 over 6 x cubed. Okay, what about P4? P4, when we put it in, we're going to get, it's sort of like the P2, P sub 2, we're going to get 1x minus 1 over 6 x cubed. That's the P sub 3. And then we're going to add to that f fourth prime of 0 over 4 factorial times x to the fourth. But we know that f4 of 0 is just 0. So this whole thing is just 0. So we don't add a term, so P4 doesn't really exist. It doesn't, it's not that it doesn't really exist, it doesn't exist. So let's do just one more polynomial of degree 5. We have the 1x minus 1/6 x cubed plus f of 5 of 0 over 5 factorial x to the fourth. And f5 is 0, we get 1. So this would equal 1x minus 1/6 x cubed. And f5 of 0 is 1, so plus 1 over 5 factorial. 5 times 4 times 3 times 2 is 120 x to the, and this should have been a 5, x to the fifth. And that's getting a little sloppy in there, so let me clean that up. This is x to the fifth, and this was a 5 factorial. So that's my polynomial degree 5. And what we notice, what you should start seeing is that we skip the even degrees. So we skipped 2 and 4 and 6. And then the odd degrees are oscillating between 1, -1, 1, -1. So we're going to get this minus positive going on. Adding a term, subtracting a term, adding a term, subtracting a term. And this is what, here we have in red, we've got our graph y equals sine x. We know that P1 up here, P sub 1, if we look back at our graph, P sub 1 was just 1x. So here we have the graph y equals x. And P3, well, going back to P3, P3 was 1x minus 16x cubed. So rewriting that, I'm going to write it as negative 16x cubed plus x. And I'm writing that way so it's in descending order. We see that we have a negative leading coefficient. So that's why it makes sense that our graph looks as it does. And then P5, well, our P5 value, which we got at the end down here, was P5 was 1 over 120 x to the fifth minus 16 x cubed plus x. And so we've got a fifth degree with a leading coefficient that's positive. So our P5 makes sense. But really, focus in. I want this to be really clear. Focus in that we're looking at approximating sine x. We're approximating sine x around x equals 0. And all these polynomial functions are doing a very good job at that. But the bigger the degree, the better it does. So again, the focus of what we're doing right now is taking any function, in this case sine x, and doing a Taylor or Maclaurin approximation of the function. Let's do one more. So we have y equals cosine x. This is very similar to sine x, but it's going to, instead of operate on odd degrees, it's going to operate on even degrees. So what I mean by that. In order to do this, what we know is that Pn of x equals f sub 0. We're doing this around x equals 0. So f of 0 plus f prime of 0 x plus f double prime of 0 x squared over 2 plus f triple prime of 0 times x cubed over 3 times 2 plus dot, 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 dot. So we need to find some of these values. Let's go ahead and do that. We know that f of 0, given that f of x equals cos of x, f of 0 would be 1, because cos of 0 is 1. F prime of x is negative sine of x, and negative sine of, so therefore f double prime of 0 would equal sine of 0 equals 0. And if we get all these derivatives, and I think this is a good idea, which is to get all the derivatives first before you start doing any of the work, just so that you can have those to depend on. So f double prime of 0 equals negative cos of 0 equals -1. And I'm going to go out and fill out a couple of these derivatives. I'm going to pause it and write them out just because you don't need to watch this. So I went ahead and derived all the way down to the sixth derivative. And again, this is sine or cosine. So it's going, cos to negative sine to negative cos to sine to cos. So it's just going to oscillate back and forth between this 0, -1, 0, 1, 0, -1, 0, 1, 0, -1, 0, 1. So that's the way we can get the derivatives. So I'm going to pause this video, and we're going to have one more video that sums all of this together.